Go ahead, take a deep breath. You feel that? That simple act connects you directly to a planetary revolution that happened over 400 million years ago. We're about to go on a journey to unravel the incredible story of how our world got the very air we need to survive. The air all around us, it's about 21% oxygen. It feels so permanent, right? Essential, a given. But, for most of Earth's history, it wasn't like this at all. So the big question is, where did all this oxygen come from? Well, the answer takes us to a planet that was, by our standards, completely and totally alien. Okay, so let's hop in our time machine. We're going back to the Ordovician period, which kicked off around 485 million years ago. And trust me, this was not the Earth you and I know. It was a world just waiting for a revolution. I mean, just look at this map. It's almost unrecognizable, isn't it? The continents are all over the place. Most of what would eventually become North America, Europe, and Asia, they were just scattered across the southern hemisphere, kind of clustered around this giant supercontinent called Gondwana. And the conditions? Well, they were harsh, to put it mildly. The atmosphere had incredibly high CO2. We're talking maybe 8 times what it is today. But oxygen was way down, sitting at around 14%. The oceans were like a hot bath, and because hot water can't hold on to much dissolved gas, they were seriously poor in oxygen. This world just couldn't support big, active, complex animal life. But then, something truly revolutionary happened. A brand new kind of life began, an invasion that would fundamentally re-engineer the entire planet from the ground up. Around 470 million years ago, the very first plants finally made landfall. Now, don't go picturing towering redwood forests. No. These were humble, almost pathetic-looking moss-like organisms, just clinging to bare rock. But the fossil evidence, the tiny spores they left behind, shows they were spreading, and they were about to change everything. You heard that right. These tiny plants, which were probably no more than a green fuzz on the rocks, were actually planetary engineers in disguise. They were kicking off a terraforming project that would alter Earth's climate and atmosphere for good. So, how in the world did they pull it off? Well, the process was this incredible one-two punch of biology and geology working together to literally rewrite the chemical recipe of the air itself. See, if you want to permanently boost the oxygen in the atmosphere, photosynthesis alone won't cut it. You have to stop the other side of the equation, decay. Normally, when a plant dies and rots, it just uses up the oxygen it created. But what if you bury that plant before it can rot? Then you trap its carbon underground. It's like putting carbon in a geological jail cell, which leaves a net surplus of oxygen out in the atmosphere. And this is why those first land plants were such absolute superstars. They were packed with carbon, but really poor in another key nutrient, phosphorus. Their carbon-to-phosphorus ratio was something like 20 times higher than the algae in the ocean. What that means is, for every little bit of phosphorus they used, they could build and then bury way more carbon. They were just ridiculously efficient oxygen-pumping machines. And this whole thing created this brilliant, powerful feedback loop. The plants, they'd actually secrete acids to break down the rocks to get at that precious phosphorus. This weathering of the rocks released more nutrients, which then fueled more plant growth, which led to more carbon getting buried, which meant more oxygen. It was a self-accelerating engine of planetary change. But hold on, the plants weren't acting alone. At the exact same time, plate tectonics was giving them a massive assist. A huge mountain-building event called the tectonic orogeny was pushing up a whole new mountain range. And get this, these new mountains popped up right in the tropics, the perfect location. Why? Because warm, wet conditions massively speed up a process called silicate weathering. You can think of this geological process as a giant air scrubber, pulling enormous amounts of CO2 straight out of the atmosphere. So you had plants burying carbon and mountains scrubbing CO2, a total 1-2 punch for global change. So how do we know this really happened? We could actually see the chemical fingerprint of this whole transformation right there in the rock record. Around 445 million years ago, the ratio of carbon isotopes found in limestone just permanently shifts. That jump is the telltale signature of a massive, sustained increase in carbon burial happening on a global scale. It's the receipt. And if you want the smoking gun, well, here it is, literally. Fossil charcoal starts appearing in the rock record for the first time. Why does that matter so much? Because natural wildfires simply cannot ignite and spread unless atmospheric oxygen is above a certain threshold, about 15 to 17%. Before this point, the world couldn't burn. After this point, it could. This is the definitive proof that the air had finally become rich with oxygen. So this new, cooler, oxygen-rich world didn't just change the chemistry of the planet. Oh no. It set the stage for an absolute evolutionary explosion. So let's just recap this planetary makeover, shall we? Oxygen levels start climbing towards the 21% we have today. CO2 levels plummet, which causes the whole globe to cool down. And those hot, stagnant oceans, they finally became cooler and could hold enough oxygen to support totally new kinds of life. And that is exactly what happened. The research connects these dots perfectly. It wasn't just a coincidence. These cooler, oxygenated oceans created the absolute ideal conditions for an explosion in animal diversity, an event so big we call it the Great Oxygenation Biodiversification Event. Ultimately, this ancient event created the very conditions necessary for the evolution of animals like us. Think about it. The high-energy lifestyles of big, mobile predators, and eventually intelligent life. That's only possible in a world with lots and lots of oxygen. So let's just run through that incredible transformation one more time. It starts with those humble little plants 470 million years ago. By 445 million years ago, the entire carbon cycle is permanently altered, and oxygen starts to climb. By 420, the world could actually burn. And by 400 million years ago, the atmosphere we know and depend on today had finally arrived. Just stop and think about that for a second. The life-giving oxygen in the very breath you just took, it was put there by the combined efforts of ancient moss and colliding continents in a process that wrapped up 400 million years ago. We are literally living inside the atmosphere that they built. Those first humble plants completely re-engineered an entire planet. They created a world where complex life, a world where we could thrive. Which kind of leaves us with one last big question to think about. What legacy will our era leave for the planet?